Good evening, everyone. My name is Jyoti Sharma, and this is last lecture, last live session. So this is week 13, and let me give you my brief introduction. I'm a PhD student from ISO Bhopal, and I did my BSc from University of Delhi, MSc from Forest Research Institute, Dehradun, and I have qualified UGC JRF, ICAR JRF, and serious exams. And right now I'm the PMRF Research Fellow. Because this is the last session, so I will try to cover everything, whatever we have discussed till now from week 1 to week 12. And so let me give you the brief discussion what we discussed, what we learned till now. So from starting, we started with the week 1, and we tried to understand the concept of acid, base, and salt, and then how we can identify that particular acid is strongest one or the weakest one, or like the same applies with the base. Then how we can create the buffer solution, how what different indicators we have by which we can identify whether the solution is acidic or basic in nature. Then in week 2, we try to understand the concept of chemical equilibrium. So when the rate of the formation of the product is equal to rate of the formation of the reactant. Based on that, we try to solve the numerical questions on chemical equilibrium. Then we went to solubility and the solubility product. We again I will try to solve 1 2 question on chemical equilibrium, solubility, and solubility product. Then we have discussed activity and Lee's Chatelier principle. Again, I will try to discuss briefly about this topic. Then week 3, we try to learn what do you mean by reaction kinetic, what's the difference between reaction rate and reaction order, molecularity. Again, we will try to see this, but very briefly with 1 or 2 question. Then in week 4, we discussed a reaction mechanism, rate determining step, as we discussed that the slowest step will be the determining step for the to determine the reaction rate. Then we saw the role of catalyst and enzyme to reduce the activation energy. So in that week, we learned about enzyme, about catalysis and activation energy. Then in week 5, we started with the radioactivity, and we learned something about nuclear chemistry. Again, I have 1 or 2 question based on this radioactivity and nuclear chemistry. Then in week 6, we try to understand nitrogen chemistry. So we in a very elaborated way uh, discussed nitrogen cycle, what different type of bacterias we need, what different phenomena and processes we have under this nitrogen cycle. Then we also discussed about the chlorination and disinfectant, then how different species of nitrogen can be the part of disinfectant, and we can do the chlorination. So we discussed about this. So from week 1 to week 6, it was the part of the environmental chemistry. And then we went to week 7, and this week 7 started with the microbiology. And here first we started with the introduction of the microbiology, and how microbiology means you have microbes, organism that are very tiny, and if you are studying that, so this will come under the microbiology. And we had like these tiny microbes such as bacteria, fungi, algae, protozoa, and viruses. Then we came to cell chemistry, biology, and microscopy. So how we can see the cells, how we can count the number of cells, and we particularly tried to differentiate whether it is negative bacteria or positive bacteria. So we tried to understand that. Then in week 9, we had microbial metabolism. How do they respire? How do they photosynthesize? How the microbes take input in it. So we try to discuss that as well. In week 10, we try to discuss the microbial growth and control. Means the one of the important law that we had was the monad law, in which we try to understand the rate of the formation of microbes and how microbes can die with what rate. So we try to understand that as well in week 10. Then week 11 was related to the pathogen and disease. So different microorganism can give you different type of disease, and this microorganism can be a vector, this microorganism can be parasite. So we in a very elaborated way talked about such kind of microorganism that can be act as the pathogen. Then in week 12, we discuss the metabolism, diversity, and biogeochemical cycle. So here we discuss again nitrogen cycle, then phosphorus cycle, sulfur cycle, iron cycle, and a lot. So we discussed a lot about microbiology. So this is how we completed the syllabus from week 1 to week 12. But this is the extra class where I will try to take the question from few question from week 1, few question from week 2, and so on. So because we have 2 hours, so we will try to solve as much as question we can solve. And otherwise, like my slides are always available on nptl, so you can go through that. You can watch the videos to see the content of each week separately. So let me start with the first question, and this first question is like, because chemistry is mostly based on the chemical concentration, and this chemical concentration can be determined in the form of molarity. So my first question is very basic, and that is molarity is measured in, and I have four options: gram per liter, mole per liter, kg per liter, and all of the above. Uh, so the answer will be mole per liter. And let me tell you again, because we are we will start building the concept, and then we'll go on further. So here is the concept of molarity. So molarity we can define as the total number of moles of solute in a given solution per liter. So this is very basic. We started with the molarity, and then we will go on further, so that we can, like, for each week we can have at least 2 or 3 questions. This chemistry is related to concentration of the reactant, or let's say the product. So that's why molarity is a very basic and very strong terminology in the term of chemistry. So that's why I just I put one slide on the molarity. So molarity is defined as the total number of moles of solute present in a given solution per liter. So how you will calculate this? So first you should have the number of moles of solute, and then you will divide it by the volume of the solution. But the question is again how you will calculate the number of moles of the solute. So there is a very basic formula, that number of moles is equal to given mass upon molar mass. So this is how the formula of molarity will be. Either you can say number of moles of solute per volume, or you can also say given mass by molar mass by volume of the solution. This is how you can calculate the molarity. And molarity is like, in a very general term, you can say this is the concentration of any chemical species. Then if you have two volume, then and if you have molarity of one solution, then you can calculate the molarity of another, and this is again for the volume. So if you have two molarity of two solution is given, and if the volume of the one is given, you can also calculate the volume of another solution. So this is how you can calculate the molarity. And the next question is, a solution was prepared using 20 gram of sodium hydroxide. Calculate the molarity of the given solution of sodium hydroxide if the volume of solution is 125 ml. So as I already told you, uh, that molarity is equal to number of moles per number of moles of the solute divided by the volume of the solution. So if you can see here, let me use the pen. So here, this is the mass, right? This is the mass of the solute, and this is volume, right? And the molarity will be uh, mass, that is the given mass, upon molar mass, and divide by the volume of the solution. This is how you can calculate the molarity. And because it is the sodium hydroxide, so you have to calculate the molecular weight of sodium hydroxide. So if the given mass is 20 gram, the molar mass is constant, you can calculate it, because the atomic mass of sodium is 23, and then the formula is NaOH, right? NaOH. So Na, the molecular weight of Na is near to 23, not exactly. So this is, I think, 23.5 something. Then O and H, and mostly it is the double of the atomic number. So the atomic number of oxygen is 8, then that's why this should be 16, and for hydrogen it is 1. So this is how you can calculate the molar mass. So if you have molar mass, if you have given mass, and if you have the volume of the solution, that is 125, you can easily calculate the molarity of the solution, right? A molarity means, in a simple language, this is the concentration of solution. So I have the solution. Let me show you. The answer is 4 molarity, and let me show you the solution. So just see here, the given mass is 20 gram. This is given. Then the volume of the mass is also given, that is 125 ml. And because we need the volume of the solution in liter, so that's why we have to divide it with 1000. And that's why this is 0.125 liter. Then the molar mass of the sodium hydroxide, this we can calculate as per the atomic number of each of the atom. So as I show you, so this is 40 gram per mole. Now what you need to do is that you need to calculate the number of moles. Number of moles will be given mass by molar mass, so 20 by 40, this will be 0.5 moles. And then molarity will be the moles of NaOH divided by volume of the solution. So this is how, 0.5 upon 0.125, and this will give you 4. So this is how you can calculate the molarity. This is very basic. If in case you are studying or learning chemistry, so molarity is the one of the first concept that you must understand, because every time you must have the concentration of your chemical species, and mostly it is molarity. It can be molality, it can be normality, but most of the time it is molarity. So that's why this is the very basic concept that you must understand if you are learning chemistry. Then the next concept is likewise, like you have learned molarity. The one another concept is the normality, and the difference between, or the relation you can say, between normality and molarity is, normality is equal to molarity multiplied by molar mass divided by equivalent mass. Or you can also say normality is equal to molarity multiplied by basicity. Or if your chemical species is acidic in nature, then you can say a molarity multiplied by acidity. So this is how there is a relation between these two. I have, I think, one question on this. Uh, so my the question on normality is, so the normality of 0.98% H2SO4, that is sulfuric acid solution, is, so what you need to calculate is the normality, and what is given is that this is 0.98% weight by volume H2SO4 solution. So how you will calculate the normality of this? I think like you quickly cannot calculate this in your mind. You must have pen and paper, so that's why I don't think that I should wait you to give me the answer. So so let me show you the answer. So this will be zero point 0.2 normality, and let me show you how you can calculate. So here it is given 0.98% weight per volume. It means we have 0.9 gram of H2SO4, and that is dissolved in 100 ml of solution. And if it is, so that means we people know the given mass of H2SO4, right? We know the given mass of H2SO4, and this is the volume. So if this is given, and we also know the molecular weight of H2SO4, molar mass or molecular weight of H2SO4 is 98. So you have given mass, you have molar mass, you have volume. So by this information, you can calculate molarity first, and you know that we do have a relation of molarity with the normality, right? So what you will do, first you will calculate the number of moles. So number of moles is equal to given mass upon molar mass. So this will be 0.98 divided by 98, and this is how you have the number of moles, that is 0.01. Then you will calculate the molarity, and molarity is the number of moles divided by the volume of solution in liters. So just see here, it was 100 ml. So this 100 ml we have to convert it into liters, so that's why this is 0.1 liter. And number of moles we already have calculated, so this is how we can calculate the molarity. If you have the molarity, then we have the equation, that is normality is equal to molarity multiplied by number of equivalent per mole. And because it is H2SO4, so means H2SO4 can give you 2H plus ion, right? 2H plus ion. So and you know that H plus ion is directly related to the acidity. So here the acidity is 2, because it can give you 2H plus ion. Or you can say here the number of equivalent per mole is 2. So what you have to do is, you have the molarity, that is 0.1, then you will multiply it with the you can say the acidity, or the number of equivalent per mole, and this is 2, and this is how you can calculate the normality. So till now you understood how we can calculate the molarity and how we can calculate the normality, because whenever we will go further, either it is equilibrium constant, or let's say anything, whatever formula we will face, uh, that must have the concentration of chemical species, and that concentration in most of the time it will be molarity. So you people must know what do you mean by the molarity. Okay, so coming to the next question, because first week was related to acid base, as I showed you. Let me again show you. So I show you here what we already have covered. So from week one, so I have 2 or 3 questions on this acid and base, and then we will come to chemical equilibrium and so on. So I have 2 or 3 questions from each of the week, and this is how we will try to understand whatever we already have learned till now. So come, let me go back to where we were. So we were here. Okay. So next question was, which of the following is a strong acid? So whenever there is any chemical species and you need to know whether it is a strong acid or strong base, so you must know the definition of acid and base first, and then like how you can differentiate between strong and the weak acid. So let me tell you here. Can you give me the answer? Which one is the strong acid here? So I have 4 options: HCl, then this is acetic acid, CH3COH, then lemon juice, and pure milk. So I think out of these four, you can tell me this must be HCl, right? And the answer is that the strong acid out of this four is HCl. But again, the question is how you will differentiate whether the compound or whether the formula you have is the acidic in nature or basic in nature. So I do have the formula. So whenever you have the strong acid, this strong acid will completely dissociate into its ion. So for example, it is HCl, then if it is a strong acid, then in the presence of any aqueous solution, if we are putting into any aqueous solution, or if itself is the aqueous solution, then it will dissociate between H plus ion and Cl minus. So if it is a strong acid, then we are assuming that 100% it is dissociating between ions. So HCl means it will give you the H plus ion and Cl minus ion. So if it is a weak acid, then a few molecule of HCl will be as it is, but few molecules will be dissociate between H plus ion and Cl minus. So I don't think that I should take the example of HCl, but if you are taking the example of acetic acid, then this is the weak acid. You can see here the weak acid. It only partially dissociate in water, but whenever they are completely dissociating into water, then this is the strong acid. Lemon juice is again a weak organic acid because it doesn't complete dissociate in water, and that's why it is again is not a strong acid. Then pure milk is again not strong acid enough to classify it as a strong or even weak acid. It is near to neutral. And the thing is, if we want to see the acidity or basicity, we have one indicator, that is pH. Again, we will talk about this pH as well, but just keep here in mind that if you have strong acid, it means we are assuming that it should be dissociated into its ion in any aqueous solution. Okay, so let me go further. Okay, so because I wanted to show you how we can differentiate whether it is acid or base, so 3 theories were given initially, and the first theory was given by Arrhenius, then the Bronsted Lowry, and then Lewis. And in Arrhenius, what was told that if in any aqueous solution, if any compound is giving you H plus ion, then it will be acidic, and in any aqueous solution, if it is giving you the OH minus ion, then this is basic in nature. But the thing is, the problem with this theory was that uh, there should be always an aqueous solution. If there is no any aqueous solution, you can't tell that that particular compound is acidic in nature or basic in nature, and it had a lot of limitation. And even the aqueous solution here was water. in Arrhenius. But aqueous solution can be anything, right? It can be like ammonia, or it can be anything. So this Arrhenius theory had some limitation, but the thing is that this theory uh, said that if any compound in the water solution is giving you H plus ion, then that particular molecule, that particular compound is acidic in nature. And if it is giving you OH minus in the aqueous solution, then this will be basic in nature. Then this Bronsted-Lowry gave the concept of protons. Gave the concept of protons. If any compound is the proton donor, if the proton is like that particular compound is giving you the proton, that means it is the acidic in nature. And if any of the compound is accepting that proton, that would be basic in nature. And you people know that this proton is again H plus ion, right? You can like in a very basic language, you can say the proton is nothing but H plus ion. But here they didn't talk about H plus ion or OH minus, but Bronsted-Lowry told that if the compound is proton donor, then it will be acid, and if it is a proton acceptor, then it will be basic in nature. But if we are talking about the Lewis, then they didn't talk about proton or H plus ion. That theory talked in term of electrons, and the one will be electron donor and one will be electron acceptor. And based on that, they differentiated between acid and base. I do have some concept. Let me show you the content. Okay, so just see here. For the Arrhenius acid and base, any compound that is able to dissociate into water, then only it will be then only the compound will be defined as acid or base. So if it is yielding H plus ion in the solution, then that will be the Arrhenius acid. And if it is a base, then it will yield OH minus. And but there had some limitation. Just see here at the end, because it states that either the H plus ion or OH ion must be present to be labeled an acid or base. However, it is not true in another theories. So it had some limitations. Next, coming to the Bronsted-Lowry theory. So here they told that if any substance is donating the proton, then it would be a Lowry acid, and if it is accepting, then it would be basic in nature. And if you know that if we are taking the example of H2O is not only accepting the proton, but it is also donating the proton. So that's why the water having the both quality. It is acidic in nature, it is also positive in acidic in nature and basic in nature. So that's why it is also known as amphoteric. And it again had some limitation, as I told you. Then we moved to the Lewis acid and base theory. So here it was that acid will be electron pair acceptor and the base will be electron pair donor. So this is how you can categorize between acid and base. So based on that, you can tell which one is base and which one is acid. Okay, and again, as I told you, we can also differentiate whether it is acid or base based on the pH, and pH is dependent on H plus ion. And Arrhenius told that if it is giving you the H plus ion, that it means it is like acidic in nature, and if it is giving you the OH minus, then this is basic in nature, right? And this pH is nothing but the minus log of H plus ion, right? So if you can calculate the concentration of H plus ion, which you can calculate the pH of any solution, then you can tell like based on that pH, and pH have like 0 to 14, and in which there is a 7, If it is below the 7, then this will be acidic in nature, and if the pH is between 7 to 14, then this will be basic in nature. So based on that, you can tell which one is the strong acid and which one is the weak acid. So here, the question is related to the calculation of the pH of the final solution. So initially, it was 20 ml of 0.05 molarity HNO3, that is nitric acid. But later on, they diluted this solution and they made that solution to 500 ml. And now they want to know the pH of the final solution. So how you can calculate? Firstly, you need to calculate the number of moles of HNO3. If you know the moles of HNO3, and then if you know the H plus ion, so the ultimate thing is that for the pH you must know the H plus ion, right? And how you will know the H plus ion? Let me show you the solution for this. The solution, the answer will be 2.6, and let me show you how we can calculate. But before that, because as I told you, pH is nothing but the minus log of your either H plus ion or the it is interchangeably with the hydronium ion, right? So you can tell like pH is equal to minus log of hydronium ion, and here you can just see how we can calculate. And then okay, so but the thing is, if the pH is given, then again you can calculate the H plus sign, right? From pH you can also calculate the H plus sign, because you can do the anti-log. So just see here, if a pH is given and you need to know the concentration of hydronium ion, then what will you do? You will do the anti-log or the reverse log, and that's how you can calculate the H plus ion concentration. And we also do have the concept of OH, POH, and this POH will be nothing but this will be again minus log of OH minus concentration. And if you are reversing that, then you can know the concentration of OH minus. And this is important. If you have pH and if you have POH, that will give you the number that is 14. Means the sum of pH and POH is equal to 14. So if POH is given and you know that the summation of these two are 14, then you can easily calculate pH. And now coming to the question, so just see here, in that question, what was given initially, it was 20 ml, right? And based on this 20 ml and 20 ml, first you will convert it into liter. So this will be 0.025 liter. And molarity is also given. Initial molarity was 0.05. Based on that, you can calculate the number of moles, because you know that molarity is equal to number of moles upon volume. So you can calculate the number of moles using your initial concentration. If you have calculated the number of moles, but here the volume has changed. Now the volume is 500 ml. So what you will do, the number of moles you already have calculated, volume has increased to 500, and this is how now you can calculate the concentration of HNO3, or you can say molarity. So you calculated the molarity when the volume is 500 ml. So this is how you calculated the molarity. But as I told you, if it is a strong acid, and we people do know that nitric acid is a strong acid, and strong acid means it will dissociate into its ion 100%. So what you can say that this is HNO3. Just see here, yeah. HNO3 will dissociate into H plus ion and NO3 minus ion. And because it is 100% dissociation, means whatever the concentration we had of HNO3, the concentration of H plus ion will be equal to the concentration of HNO3. Right. So this is how you calculated the H plus ion concentration. And if you know the H plus ion concentration, then like you are nearly to calculate the pH, because pH is nothing but the minus log of H plus ion, right? So how you will calculate, let me show you. So here, because it is a strong acid, means whatever the concentration of nitric acid we had, this will be equal to the concentration of H plus ion, because it is a strong acid, right? So this will be 0.0025 molarity as we calculated here. Then pH is equal to nothing but minus log of H plus ion, and we will put the value of H plus ion 0.0025. We will do some calculation, and then we can calculate that pH will be 2.6. And just see here, the pH value is very near to zero, different, less than 7. So it means that it is a very strong acid. So this is how you can calculate the pH of any solution. If you have any doubt, you can write in the chat box. I will try to solve the query. And if you think that you didn't understand any of the step, then you can also tell me. Or if you know that you already know the concept, that I can skip because I have a lot of slide, then I can easily skip that particular slide if you already uh, have a clear concept in your mind about that particular concept. Okay, so till now you learned pH, you learned molarity, you learned molarity, right? And here and POOH, right? So here what is given is that what you need to calculate is the pH, but right now you need to calculate the pH of the buffer solution. And you must know that buffer solution can be prepared when you have the mixture of weak acid and, let's say, weak base. Then only you can create that buffer solution. So here buffer solution was prepared by 0.05 molarity of ammonia, and that is weak base, and 0.15 molarity of ammonium chloride, and this is weak salt. So here it is weak base, and this is salt, right? This is salt of weak base, salt of weak base. So this is how you can create the buffer solution. The first condition can be, it should be weak base and the salt of weak base. And buffer solution you can also create by, if you have weak acid and the salt of weak acid. So you have like 3 or 4 types by which you can create the buffer solution. But if you have two compound, right, one is salt and another is weak base, and if you want to calculate the pH after mixing them, because it has created a buffer solution, then how you can calculate the pH here? So we will see. We do have another formula to calculate the pH of the buffer solution, and here pkb is given. So and but yes, we must understand what do you mean by this pkb. So before solving that question, I will try to uh, give you the brief explanation about what will be the formula to calculate the pH of the buffer solution. And in that formula, we have different terminologies that I also try to understand. Let me show you. The answer is 9.47, but okay, let me clear it. So like the equation is Henderson Hasselbalch equation, in which POH, so this is POH, just see here, and what we need to calculate is pH. So here POH will be equal to pkb. We will see how we can calculate this pkb, and then log of the concentration of your salt and concentration of your weak base. And this is how you can calculate. But before that, I will tell you how we can calculate this pkb. And again, we have one more terminology, that is pka. If your buffer solution is prepared by weak acid and the salt of that weak acid, then this will be replaced by pka. So let me give you a little brief explanation about this terminologies. So first I will start with the ion product of water. So because you know that water will dissociate into H plus ion and OH minus ion, and the equilibrium constant, how we can calculate, we have the product. So concentration, the multiplication of the concentration of product divide by the reactant will give you the equilibrium constant, right? And if we keep this H2O in the left hand side, then what we can do is we can tell like this K multiplied by concentration of H2O, we can give them another constant value, that is Kw, that is the ion product of water. So this Kw will be nothing but the product of H plus ion and OH minus ion, right? Now, because that particular equation to calculate the acidity or basicity of your buffer solution, we had the terminology that is pKa, or let's say pKb. So you must understand what does it mean. So for example, you have any acid and that acid is Ha, and that will be dissociate among H plus ion and A minus sign, right? And if you can write the equilibrium constant equation, then what it will be, this will be in your in your numerator, and this Ha will come into your denominator. So this upon this, and this is known as the equilibrium constant for acid, right? And if you want to calculate the pKa, this pKa will be nothing but minus log of Ka, and we have calculated here the Ka, right? So this is how you can calculate the pKa. Likewise, you can also calculate pKb. Let me show you how. So just see here, if we have any base, if we do have any base and we are dissolving into water, then it is giving you BH plus sign and OH minus sign. And here we can write the equation, the equilibrium constant equation, and this equilibrium constant equation will be known as Kb. And now from that we can calculate pKb, and pKb will be nothing but minus log of Kb. Okay, so this is how, so you got to know how we can calculate Ka and Kb, and based on this Ka and Kb, how you can calculate pKa and pKb, right? So the things are clear little bit, but let me come again. So if you have Ka and Kb, and if you will multiply it together, then you will get the ion constant of water, right? Or you can say this is ionization constant of constant for water, and the value is this value is given at 25 degrees Celsius, and this is 1 multiplied by 10 raised to power minus 14. And based on that, again, you can tell a lot of things, but I will not discuss much about this right now, because we are solving that question in which we need to calculate the pH of the buffer solution. Okay, so right now, if we how we can calculate pKa? So pKa is nothing, as I told you, this is minus log of Ka. Here I have given the one like example how we can calculate uh, pKa from Ka, and how we can calculate Ka from pKa, like the antilog. And likewise, we can also calculate pKb. I will not go deeper into it. So and just see here, so we were talking about to calculate the pH of the buffer solution. So to calculate the pH of the buffer solution, this is the derivation. If you people want to let me explain, then I can explain. Otherwise, I will just tell you that based on this derivation, we got to know that this is the formula of pH of any buffer solution if that buffer solution has the weak acid. So if that particular buffer solution has the weak acid, then this pH will be equal to pKa log 10 of conjugate base and weak acid. And let me go to the question again. This was the question, right? This was the question and this was the solution. So what we can do is, first we will calculate POH, and this POH will be pKb plus log of, this is your salt concentration and this is your base concentration. pKb is already given, that is 4.75, and these concentration are already given. So this is how you can calculate the value of POH, right? And you know that pH is equal to the summation of POH and pH is equal to 14, right? So based on that, you can calculate the value of pH. So pH will be 14 minus POH, and POH we calculated is 4.53, and this is how you can have the solution 9.47. So what till now what you understood is molarity, normality, pH, POH, then the constant of equilibrium constant for acid, the equilibrium constant for base, and based on that equilibrium constant of acid, base, and pH and POH, how we can calculate the pH of the buffer solution. So this is till now we have learned. Coming to the next solution, let's say if we do have the molarity of any solution, and if this is the weak monoprotic. So monoprotic means it will give you one H plus ion, and here this solution is 2% ionized. It means this is a very weak acid because only 2% is getting ionized. But in the strong base, strong acid, what we are assuming that there is 100% dissociation between the ions, right? And you need to calculate Ka. And we saw that how we can calculate that Ka, but here we do have like different formula how we can calculate. So here the ionization fraction is 2%. 2% means 0.02, and the concentration is zero point 0.3 molarity, sorry. And here we do have the formula. If we do have the monoprotic means if it is giving you just one H plus ion, then the formula will be the equilibrium constant for acid. This K is nothing. Equilibrium constant for acid is equal to alpha square multiplied by C. And this is how you can calculate, and the value will be 2 multiplied by 10 raised to power minus 5. If you have any problem, you can write in the chat box. Otherwise, I will try to cover as much as possible today in the summary session. Okay, again, I have the question of pH of the buffer solution, and just see here we have NaH2PO3 PO4, and here we have Na2HPO4. So one is either acid or base, and another is salt of that particular acid and base. And what you need to calculate is to calculate the pH. Okay, so what is given is that 12 gram of this particular compound is given. The given mass is given for both of this compound, right? And then pKa is also given. So pK is given means this buffer solution has been prepared by weak acid and the salt of that weak acid. So this must be acidic in nature, right? So pK is also given. So how you can calculate? Just see here. First, what we do? First, we will do calculate the concentration of first compound. The mass is given, molar mass is also we can calculate. So this is how we can calculate the concentration of acid. And the another is conjugate base, or you can say the salt of the weak acid. So here given mass is given, and then the molar mass we can calculate, and based on that we can calculate the concentration. So we calculated the concentration. Just keep in mind this concentration is in molarity, right? And again, we people know the formula that pH is equal to pKb plus log of conjugate base upon acid. And we already have calculated here the concentration of each of these. So what we need to do is we need to put into the formula, and then we can calculate, we can simplify this and we can calculate the pH, and this pH will be 7.50. So this is how we can calculate the pH of any buffer solution. Now coming to the next question. Next question is also on pH. I think we can skip. Uh, Yes, but here actually I put that question because that particular question is little different from the last question, because here we prepared the buffer solution with 300 mg per liter of acetic acid. So it means molarity of that acetic acid is given, and then 150 mg per liter of sodium acetate. After addition of, so here what we do is we added 50 mg per liter of HCl. This was not like this concept we didn't understand till now, that we can also add some acid or base in the buffer solution, and then what will be the pH after adding acid or base into that. We have buffer solution created by, let's say, acetic acid and sodium acetate, but if we are putting some another acid into that, then how we can calculate the pH of that particular buffer solution. So that's why, like, this was a little bit different from the question we till now solved. So that's why I put that question, and let me show you very fast the explanation of this. So what we will do is that for the acetic acid, we had the molarity, and that molarity was 300 mg per liter. And this was not exactly the molarity, actually this was the concentration, but this concentration was not in molarity. For molarity, what we have to do is this was just the given mass, right? So we have 300 mg per liter, then we have the given mass, and volume is also given. So what was not given was molar mass. So if we will divide with the molar mass, then we will get the molarity. So we got the molarity if we are divided it to dividing it with the molecular mass. So we got the molarity of acetic acid, we got the molarity of sodium acetate based on the information, because here 300 mg per liter is given and 150 mg per liter is given, means given mass and volume is already given, and if we people know the molar mass, then we can calculate the molarity, and this is how we calculated the molarity. But here what we did is we added 50 mg per liter of HCl. So first what we do is we will calculate the concentration of this in molarity. So this will be 4.11, and then here the thing is very simple. If we are and this HCl is very strong acid, and strong acid means whatever the concentration of HCl we have, the H plus ion concentration will be exactly same as the concentration of HCl, right? So now we know the H plus ion concentration. So H plus ion concentration will be same as the concentration of HCl. Then let me clear it. Then we people know that how we can calculate the pH of the buffer solution. So first we calculated the pH of the buffer solution, and this buffer solution pH is 4.30 based on your acetic acid, sodium acetate, and their concentration. Based on that concentration we calculated. And then but here the extra concept was that before, here we were calculating, we were adding HCl. So this HCl will react with CH3CO, that will form the acetic acid. So the amount of H plus ion added we already have calculated. So this much H plus ion we will create or we will add. So if we will add, and if it will react with this CH3CO, it means it will decrease the concentration of CH3CO by 4.11. So it means you have to subtract. So here you just see here, this will be reduced because we are putting H plus ion, and that H plus ion will neutralize that conjugate base. So it means if we are subtracting this, now the concentration will change and concentration will be this one. But because the concentration of this one will increase, because we are adding H plus ion, and this will be increased by the this number whatever we had the concentration of H plus ion. So this is how you have right now the new concentration of your acid and new concentration of your conjugate base. Now what you need to do is put here these values, and then you will see the pH value has changed. Okay, so this is how you can calculate the pH of any buffer solution if something is added later into that buffer solution. Now, this is very simple question. You need to calculate the pH when you do know the concentration of OH minus, because we know that if we have pH and if we have POH, and if we are doing the summation of these two, then this will give you the 14. Then it means from this OH minus ion you can calculate POH, and if you know that POH, so then you know that pH and POH is equal to 14. So you can easily calculate the pH value if OH minus concentration is given. So how we can calculate this? Let me show you. So this is how you can calculate. You have the concentration of OH minus, and then, and you know that there is again one more like equation. The concentration of H plus ion and OH minus will be equal to 10 raised to power minus 14, right? And just put that in equation, and you will get the H plus ion concentration. So like by two way you can calculate. What you can do is, the first way can be you have OH minus ion. By that you can calculate POH, and if you know the value of POH, then your pH will be equal to 14 minus POH. This can be one way. Another way will can be like this. In spite of this equation, we have another equation, that is this one. If we do have just the concentration, and if we are multiplying this concentration of H plus and OH minus ion, this will give you the 10 raised to power minus 14. And just put that into equation, then this will give you first the H plus ion concentration. Then we know that pH is equal to minus log of H plus ion concentration, and this is how you can calculate the pH, and pH will be 9.3. So 9.3 means it is basic in nature, right? So this is how, like this there are two different ways by which you can calculate the pH of the water. Okay, coming to the next question. uh, Here again we have little tricky thing that has been added into that question. So initially it was 20 ml, and now it is 500 ml, and the molarity of initial solution is given, and now you need to calculate the approximate final pH. So how you can calculate this? Just see here. So we know that we already have seen that if we do have two type of solution and have different volume and different molarity or normality, then we have very simple formula. So here the formula is V1 and 1 is equal to V2 and 2. Just put everything here. So the V1 is 20 ml, V2 is 100 ml, and 1 because here the normality and molarity of HCl is same. because the acidity is 1. So molarity multiplied by acidity is equal to normality, and acidity here is 1 because it is giving you just one one H plus sign, right? So that's why uh, like the n is equal to molarity as well. So what you will do, you will calculate molarity first, and molarity, or you can say the normality, both are same for HCl. And as I told you, HCl is the strongest acid that will be dissociate completely. So whatever the concentration we have for HCl, that concentration will be equal to the concentration of H plus ion. So what we are doing, we are just putting this value for H plus ion, and then you are calculating the pH value. So this is how we can calculate. This is 2.1. Then again we have another question. I know this is again different from the question we already have solved, but because we already have solved much question on pH, then I think I should skip these questions on pH. And you can also see the question on Ka, but as I already have showed you that how we can calculate this K and Kb, so I think it would be easier right now to solve you such kind of questions. So I'm skipping it, this kind of question. Okay, the very important principle in chemistry is Lee Chatelier principle, and this is like if you are putting any kind of disturbance in the equilibrium, or if you are disturbing the reaction, then your equilibrium will be shifted either left or right based on whatever kind of perturbation you are putting into that reaction. So this is, if one of the condition of the system in equilibrium be altered, the system will adjust itself in such a direction as partially to neutralize the change in condition. And it can be like if you are changing the concentration in the, let's say if you are changing the concentration of the product, then the equilibrium will shift in left or right based on like how you are changing the concentration. If you are changing the temperature, or if you are changing the pressure, then this will shift the equilibrium to the side whichever will neutralize the change in condition. So this is the Lee Chatelier principle. Okay, the another question is on solubility product constant. So here the solubility product constant for a particular compound is given, that is 1.2 into 10 raised to power minus 22, and you need to calculate the pH of that particular compound when it will begin to precipitate. So here again we have another terminology, and that is soluble product constant. So I have little content on how we can calculate equilibrium solubility product constant, and then we will try to solve this question. So just see here, this is the content that I put. So if we do have any compound AB, and if this AB is dissociating and have the equilibrium with A plus ion and B minus ion, so and that will when AB dissolve in water, then what we are assuming that if the S is representing by the molar solubility of AB, and here if they are in equilibrium, so if they are in equilibrium, then what we are assuming that the concentration of A plus will be S mole per liter, and the concentration of B minus will also be equal to S mole per liter, and Ksp is equal to the multiplication of concentration of A plus ion and B minus ion, and these are S and S. So this is S square, and the solubility is equal to the square root of your the square root of solubility product, right? So but this is the formula when you have uh, just H A plus ion and B minus ion. But let me show you another. But if you have the solution or the compound like this, KAF2 means you have 2 mole of fluoride and 1 mole of calcium ion, right? So here, no doubt we are so here the concentration of calcium will be S, but the concentration of fluoride will be 2S but not S. And if we are putting this S and 2S, then this will give you 4S3, and here the solubility will be equal to 4 multiplied by the constant and raised to power 1 by 3. It means based on the compound, you the formula of the solubility is getting changed. Likewise, we have another formula. So if we have here 3, if we here we have 3, it means here we have 3. So here the formula will be 3s raised to power 3, then s, and this will give you the 27 multiplied by solubility raised to power 4. And this is how the formula is getting changed for the solubility. For the salt, that salt have A3x, right? So this is how you can calculate the solubility. Now coming to my question, and that question was the compound was DY and OH had 3 in the bottom. So it means this the equation will be like this. And as I told you, here this will be S, and here it will be 3S. So S, 3s and 3s raised to power 3. So here the solubility product will be equal to 27 multiplied by s raised to power 4, and solubility here we can calculate like this. And solubility is given, then we can calculate solubility product is given, then we can calculate the solubility like this. Okay, if you I'm little fast, I know, but I wanted to cover everything, but I don't think that I will cover. But let's see how much I am able to cover. So this is how you can calculate the solubility. And because in that question we need to not only calculate the solubility but the pH. So here what we can do is, in that equation we had OH, right? Let me show you. So here we had the OH, and this OH is equal to 3s, right? So just see here, this OH is equal to 3s. So we can calculate the OH minus concentration. If we do know the OH minus concentration, we can calculate POH from that. And if we do know the POH, then we have again one equation, that is pH plus POH is equal to 14. And this is how you can calculate the pH of that particular formula. I think I should skip this. No doubt this is different because we are adding two things together, but let me skip this. Otherwise, I will be only on first or second. So just keep in mind, we have the common ion effect on solubility as well. So in that common ion, the solubility will not be just S square, but in that particular case, we have this X that will be added. And this X, let me show you, X is the here they must have given. So X is the concentration of H plus that will be added from another compound that have the common ion. So this is how like the solubility formula will be sorry, solubility product formula will be changed whenever you are adding another compound that have the common ion. So this is how you can solve. I'm not going further into this. So this is how you can just see the solution, how we can calculate this. Okay, so next coming to the rate law. And here my question is on the reaction order. This is again very important. We are now jumping on another week. and I think this is third week content or second, I don't remember. But here we need to calculate the reaction order. And okay, so the question is how this reaction order, that is M and N, in the rate law equation determined. So this is the rate law equation where R is equal to K multiplied by the concentration of A raised to power M, and multiplied by uh, concentration of B raised to power N. But how we can calculate this M and N? This M and N are nothing but the reaction order. So how we can calculate this? We can't calculate it by the stoichiometric coefficient, but we have to calculate it by the experiments. So B is the right answer. How we can calculate this? So just see here, for the reaction rate, if you have any doubt, you can like ask me anytime. You can write in the chat box. I know I'm little fast, so maybe uh, you are not like understanding much content. But whenever you have any problem, you can write me in the chat box. Okay, so the rate reaction. We already know that this is the speed at which reactant are converted into product, right? And if we do have this reaction formula, this is small letter, or you can say this is the number of moles, or the stoichiometric coefficient. Exactly, this is stoichiometric coefficient. Then we can the rate reaction will be like this, right? With the time, how the concentration of A is changing, and here the coefficient will be in the denominator, or it will be also equal to how the concentration of B is changing with the time, but it will be multiplied by minus 1 by B. And likewise, from any of the concentration changing with the time, we can calculate the reaction rate. And let me show you. Okay, the main thing that we need to understand is this is the reaction rate, and this is equal to K. And this equation, we have the concentration of A and B, and we have the exponent M and N. And here, this M and N are the reaction orders. And this reaction order we can't calculate like by equation only, but we have to calculate it experimentally. So okay, so based on the background that till now I discussed, then the another question is, what is the key difference between molecularity and reaction rate? We have four options. Molecularity is determined experimentally, while reaction order is theoretical. B is molecularity refers to the number of reactant molecules involved in an elementary step, while reaction rate is determined from rate law. C is molecularity applies to overall reaction, while reaction order applies only to elementary step. And D is reaction order is always an integer, while molecularity can be fractional. So the thing is that you uh, must have to understand that what's the difference between molecularity and the reaction order. So this is, molecularity is the number of the reactant molecule involved in any elementary step, whereas reaction order is determined from rate law. I will show you. So this you already know. Okay, so this is important. There is a difference between order of reaction and molecularity. So the definition is, order of the reaction will be sum of exponents in rate law. So this is the exponent. This is 2, this is 1. So order will be 3. But here, molecularity is the number of molecule involved in an elementary step. You just see here, if it is the if this is the elementary step, and here the number of molecules, so the one molecule of A and one molecule of B is giving you the elementary step, then here the molecularity is equal to 2. How we can determine? So rate of reaction we can determine experimentally, but the molecularity we can calculate theoretically. if we see the possible value, then order of reaction can be zero, can be fractional, or it can be whole number. Just give me 1 minute. Sorry for the disturbances. Okay, so we were discussing the possible value. So this possible value can be zero, fractional, and whole for order of reaction, and it will always be the whole number for molecularity of the reaction. And order of the reaction can be applied both to elementary and the complex reaction, but molecularity can be only applied to elementary reactions. So these are the few differences between order of reaction and the molecularity of reaction. Okay, the another question is there any correlation between the stoichiometry representation and molecularity? And if we see here, let's say if it is a and plus, let's say b is giving you c, and let's say this is 2a plus b is giving you c, then is there any correlation between stoichiometry representation and molecularity? So stoichiometry representation, it may be easily we can calculate this stoichiometry representation using the equation. So in that equation we used 2 moles of a and 1 mole of b, then it means it is the stoichiometry representation is giving you 3. Okay, so this is the stoichiometry. But if we see the molecularity, it may be that in the elementary step 1a is is uh, giving is reacting with 1b, and this is giving you, let's say, ab, and then ab is reacting with a, and this is giving you c. Okay, so the reaction was completed in 2 steps, but this is the elementary step, this is the first elementary step, and in that first elementary step this is 1, this is 1, so molecularity will be 2. In that elementary step, here this is 1 and this is 1, here the molecularity will be 2. So in stoichiometry, we have completely, if we do have completely balanced equation, then we can easily calculate the stoichiometry representation. But molecularity is dependent on the elementary steps. If we know the elementary step, then we can calculate the molecularity. But just see here, there is no any correlation between these two. So the answer will be no correlation. So answer will be no correlation. And you can just see here, if we see the stoichiometry representation of H2 plus O2 is giving you H2O. So here this was the 2 molecule reacting with the 1 molecule and giving you the 2 mole. And this is not giving you the information how the reaction mechanism or how many molecule react in each step. In each step, it will give you the molecularity, right? But not the stoichiometry representation. So, and the if we see the molecularity, then molecularity, this we already have discussed. So, I think the things are clear how molecularity is different from how this is different from your stoichiometry equation, right? Okay, again, I have one table that will differentiate how stoichiometry representation is different from the molecularity. So if we see the definition, then balanced chemical equation that is showing you the reactant and product. So here this is 2, this is 1, and this is balanced equation. So in that balanced equation, you can tell the stoichiometry representation, but molecularity is in each of the elementary step, how much molecules are involved, that will give you the molecularity. So By balancing the chemical equation you can calculate the stoichiometry, but by analyzing the reaction mechanism you can calculate the molecularity. So molecularity and stoichiometry is different, but just keep in mind, if we are just talking about the elementary reaction, then we will talk about the molecularity, but if we are talking about the balanced equation, then this will be stoichiometry representation. So this is how we can give the difference between these two. Okay, so the next question is, what is the unit of rate constant K for a zero order reaction? We already talked about the order reaction. So what we got to know that here this R is the reaction rate and this R is equal to K. This is one constant, and let's say this is A, or this is A, and then raised to power m and b raised to power n, and this m and n is giving you the reaction or order of the reaction. And if this order of reaction, this m and m is equal to 0, then we will call this is the zero order reaction, right? But what will be the unit of K? So if this is giving you the 0, if this is giving you 0, and you know the unit of R, then easily you can calculate the unit of this K as well, right? And if it is a zero order reaction, let me show you how we can calculate. So this will be molarity per second, and I must have some explanation for this. So how you can do this? So rate is equal to, you know that rate is equal to the change in concentration of any chemical species. So if the concentration of reactant A is Ca, and if it is changing with the time, then this will give you the rate, right? And negative means the A is decreasing over the time. And okay, so the next thing is that this change in the concentration of A species with the time is proportional to the concentration of A raised to power n. And this raised to power n is nothing but the reaction order. This is reaction order. So just keep in mind, this is our final equation. So if we have zero order reaction, keep this zero, and then calculate and then you can tell the SI unit of this one. If let's say the concentration is raised to power 1, then the K value will change. If here the value is 1, or if here the value is 2, then the unit of K will change, because this is constant, this is changing with the time. If this will be changing at the time, it has to change. So the SI unit for different order of the reaction of the constant will change. So let me show you how we can do this. Okay, so these are the rate, law, and integrated form when we do have zero order reaction, first order reaction, and second order reaction. Okay, the next question is, which of the following statement is true about the slope of the linear plot for different reaction order? So what we have is, as I told you, the n value will change for different order reaction. This can be 0, this can be 1, this can be 2, and the raised to power or the exponential value, if it is changing, then it means the integrated form of that equation will also change. And in that integration form, if we are plotting the concentration of the reactant changing with time, so in the, let's say in the y-axis we have the concentration, in the x-axis we have the time, and how it is changing with the, how the concentration is changing with the time, if we are plotting that, and if the order reaction that was in exponential, if it is changing 0, 1, 2, then this will give you different type of plot. It can be straight line, it can be like exponential, or it can be horizontal or vertical. So based on that, we can also tell whether it is zero order reaction, first order reaction, or second order reaction, right? So let me show you. So here the answer will be, the slope will be negative for first order reaction, but it will be positive for second order reaction. Let me show you here. So because we saw the integrated rate laws, so this is for zero order, this is for first order, and this is for second order. And what we are doing, we are plotting this one against time, this one against time, and this one against time. So just see here, if in the first order reaction the slope will be minus k, and in first order reaction the slope will be again minus k, but in second order reaction the slope will be uh, positive k. Just see here. And based on this equation, based on this integrated rate law equation, we can also calculate the intercept. So in zero order reaction, the intercept will be A0. For first order reaction, this will be, so you people must know that what do you mean by intercept. So intercept means this part. Part will be intercept. This part will be your intercept. So this one. These are the intercept. These are the intercept. So from that integrated rate law, we can calculate, and if we are plotting linear plot, then we have some slope value and we have some intercept. Based on that slope value and intercept, and whether it is a versus t, or natural log of a versus t, or 1 upon a versus t, we can calculate, or we can tell, or we can determine what kind of order reaction we are talking about. So this was about the order of the reaction. One question I put here based on Beer-Lambert law. So this question is, according to Beer-Lambert law, the absorbance of solution is directly proportional to what? Options are only the thickness of the solution, B is only the concentration of absorbing species, C is both the concentration and the path length of the solution, and D is only the intensity of incident light. So just keep in mind that if any solution, if we have any solution, and that solution, and if any kind of light is giving to that particular solution, then how that light is getting absorbed by this solution based on the intensity. So initially the intensity of light was, let's say, I node, and here, because let's say the concentration was so high, that means the new I will be lower than this I node, right? So based on this principle, we can calculate what can be concentration of this compound. So so the equation is given by Beer-Lambert law. So based on absorbance, how much absorbance has been done by this compound, we can calculate the concentration of that compound. And this is dependent on both the concentration and the path length of the solution. Let me show you this. I must have, okay. So according to Beer-Lambert law, absorbance is equal to epsilon multiplied by the concentration of the absorbing species, and L is the path length of the absorbing medium. And this is how you can calculate. So the key concept is that absorbance increases if either concentration or path length increases. So that's how, if we have some concentrate, if we do have some solution, we can calculate the concentration based on how much light has been absorbed or how much light has been emitted by that particular solution. So this has been given by the Beer-Lambert law. Okay. So, coming to the next question, I think we have jumped into third or fourth week right now. So, according to Van 't Hoff rule, how does the reaction rate change when the temperature is increased by 10 degrees Celsius? So, the thing is, if we are increasing the temperature, then what kind of impact it will have on the reaction rate? How reaction rate will change whenever we are increasing the temperature by 10 degrees Celsius? So the answer is it doubles. So your reaction rate will double whenever we are increasing the temperature by 10 degrees Celsius. So just see here the explanation. This rule state that for many chemical reaction, this is not a like very universal rule, but for many chemical reaction, the reaction rate will approximately doubles for every 10 degrees Celsius increase in temperature. And this is because whenever you will have the high temperature, this will give you more energy to the reactant molecule. More energy means more frequency and effectiveness of the collision. So if there will be more collision means rapid reaction rate. So this will be doubled. Okay, the next question is on the activation energy, because one of your unit was based on catalyst and enzymes, right? And the basic concept was that if you are adding any catalyst or any enzyme into any kind of solution for the reaction, that will reduce the activation energy of that particular reaction, and that's how the reaction can be completed very fast. Okay, so the concept is very basic. Just add catalyst or any kind of catalyst or enzyme that will reduce the activation energy. Whenever activation energy will be reduced, the reaction will be completed so fast. So here the question is, but what do you mean by the activation energy? What does the activation energy represent? So this is the difference between activated complex and the reactant. Just let me show you here. So you have any let's say in for the reactant you have some energy, but for the reaction to be happened you need some energy, and an energy up to this level. And so it means energy you have initially with the reactant, and this is the complex that has been created here. So the difference between the energy of the reactant and the complex is giving you the activation energy, right? And if you have any kind of catalyst or enzyme, that will reduce that activation energy, and that will give you the reaction very fast. Okay, and this is uh, activation energy is same, but whatever the energy we have of the product, that will decide either it will be endothermic reaction or exothermic reaction. You can read more in my previous week slide how this can give you different reactions. But just see here that it is the difference between activation complex and the product. Okay, coming to the next reaction, next question, and this is okay. But in activation energy, we were talking about the catalyst, right? So, what type of catalyst is used to slow down? Till now, we talked that if we want to increase the reaction speed, right, we need catalyst, but we also have some catalyst that can slow down the reaction. So, for example, if we are keeping hydrogen peroxide as it is in a very ambient temperature and pressure, with the time this hydrogen peroxide will react with the oxygen we have in the atmosphere, and that will give you this will release water, right? So but if we want to slow down this decomposition of hydrogen peroxide, and if we want to the strength of hydrogen peroxide, then we must have to have some catalyst that can slow down this, right? So what kind of catalyst do we need? is it a positive catalyst, or is it is a negative, or it is a auto, or it is a enzyme catalyst. So if we want to slow down the decomposition, we need the negative catalyst. If we want to fasten the reaction, then we need the positive catalyst. If some reactant itself is increasing the speed of the reaction, then it means this is nothing but the autocatalyst. And enzyme catalyst is the organic form of the catalyst that is made up of the proteins. Then it will be enzyme catalyst. So here the answer is negative catalyst. I do have the explanation, but I don't think that I should go further into that because I already have explained. Okay. The next is, initially we use the petrol, and right now what we are talking about is that we need the petrol that is lead free or lead free. Then why we are then like why there is any change? Initially we were using the lead petrol, and right now we are using the lead free petrol. Then how this happened? The question is related to that only. So why is unleaded petrol used in automobile with catalytic converter? So initially in the vehicle we did not have the catalytic converter. That catalytic converter helps to complete the combustion in any automobile, right? And if we do have any lead in that petrol, that lead will block the active site of any catalytic converter, and that's why the complete combustion or complete conversion of the compound into harmless species will not be happen if we do have lead in our petrol. So just okay, so what you can do is you can read about the catalytic converter. That is very important from the perspective of net exam if you are appearing in the environmental sciences, and you people must know that what kind of catalytic converter we are using in the vehicle and why we do not need lead right now in the petrol, but we are using lead free petrol. So you can like little bit read more about this. Okay, we are like moving very fast to another week, and the one question is related to the blue baby syndrome, and this is methemoglobinemia, and this is one kind of syndrome that is happened in the new baby born, and because of the drinking water. So you have to tell me uh, because of what contaminant in the drinking water can cause the blue baby syndrome. And this blue baby syndrome means you have hemoglobin, right? But that hemoglobin will not attach with the oxygen, but some another compound will attach to that hemoglobin, and based on that this the baby will turn into blue because the oxygen is not attached to the hemoglobin, right? So that's why this will give you the blue baby syndrome. The baby will appear as blue colored. So this can be due to nitrate. Just see here. Um, so whenever you have the excessive amount of nitrate in your drinking water, and that will be converted to nitrite in the digestive system of the baby, and that nitrite will react with the hemoglobin, will form the methmoglobin, and which will not carry the oxygen. And if there is any deficiency in the oxygen level in the blood, that's how it will give you the blue color of the baby, but not the red or the pink color that baby mostly have that color. So this is the blue baby syndrome. Now coming to if you people know that if we do have any uh, water body, let's say we have lake, let's say we have pond, or we have river, the health of that particular water body we can check using one of the indicator, and that indicator is dissolved oxygen. If you have dissolved oxygen near to 40 mg per liter, then you can say like your water is healthy. Or if the DO, dissolved oxygen, is less than, let's say, 14, and it is near to 5 or 6, then it means some organic matter has been added into your water, and that is giving you the contamination, more organic matter, more microorganism you have in your river body. So but again, if the indicator for the health of your water body is dissolved oxygen, then how we can calculate this dissolved oxygen? We have different reagent by which we can calculate. Now you have to tell me out of Winkler reagent, Nessler reagent, molybdenum molybdate reagent, and the barium chloride. So whenever you want to test the dissolved oxygen in water, so the reagent is Winkler reagent. So you can use Winkler reagent to determine the dissolved oxygen in your water bodies. Okay, but if you want to determine the hardness of the water, then you will use DTA. DTA is the one reagent that can help you to determine the hardness of the water. Okay, now we are switching to another week, and that week talked about the radioactivity. So, and here, how you will identify whether your particular atom, particular molecule is radioactive or not, and this can be based on atomic number. The question is, you need to tell the true statement when your element have the atomic number greater than 83. So whenever atomic number is greater than 83, then you will consider that particular element under radioactive, and that particular element will undergo decay. So the very basic definition, or very basic definition to differentiate whether your element is radioactive or not, it can be based on the atomic number. So if the element have the atomic number greater than 83, then you can consider that particular element as radioactive in nature. Okay, then there is a kind of relationship between average life and half life of the radioactive species. Average life is how many years that species will survive. So for example, if you have C14, so this C14 will be changed into another, let's say, will be changed into C12, right? But how many years it will take to change from C14 to C12, because C12 is not radioactive. So the average life will be like that. But the half life is, let's say you have 100 nuclei. So to change, like whenever the 50% of that nuclei will decay, then we can say like how much time it took. So this is the half life, and there is the relationship between these two, average life and half life. This is, the average life is equal to 1.44 multiplied by your half life. And so based on that particular equation, you can tell. Okay, based on that, I have one question, one numerical question. So let's say you have a 0.004 gram sample of thorium, and you people know the half life of thorium, that is 1.4 into 10 raised to power 10 years. Then can you calculate the rate of disintegration? So how you can calculate? The answer is B, and let me show you how. You know that decay constant is equal to 0.693 divided by half life, and half life is given. So based on this equation, you can calculate, based on that. Okay, half life is okay, so first you will calculate this half life from year to minute, and so if you are changing from year to minute, then this will be this much. And then you will calculate the decay constant. So decay constant is just put the value of half life into that, and then you will get this decay rate, and decay rate is the disintegration rate, right? So this will be 9.41 multiply by 10 raised to power 16 per minute disintegration per minute. So this is how you can calculate, right? Then then because you know that the number of molecules or the number of atoms we have in 0.04 gram, we can calculate it using Avogadro number. So if we have the Avogadro number, multiply by the given mass, divide by the molar mass, this is how we can calculate the number of atoms. And the activity is equal to uh, decay constant and multiply by the number of atoms that we have, and this is how you can calculate the activity. Okay, the next question is, if your element is undergoing through alpha decay, so and what will happen to the atomic number and atomic mass of that particular element? So the answer is that your atomic number will reduce by 2 and atomic mass will reduce by 4, because alpha decay means helium will release. So helium has 2 atomic number and 4 atomic mass. So whatever the compound will remain, that compound will have the atomic number less than 2 and atomic mass decrease by 4. Okay, so this is how you can tell if there is any alpha decay. So here you can just see, you had the uranium has the atomic number 92 and atomic mass 238. If there is a alpha decay, means helium is releasing, then the remaining will be thorium, and thorium have the atomic number 90 and atomic mass or mass number will be 234. Then this is again one numerical question. I don't think that I should go into that, but just most of the time you do the carbon dating. So based on the radio isotope, the isotope of the carbon, that C14 is radioactive in nature, and with the time the C14 reduces. Okay, and based on that, you can calculate that particular living organism, like what the life how many year it was survived, and like what is the lifetime of that particular organic matter, that we can calculate using the carbon dating. And this question is based on that only, but I don't think that right now I should go further into that because I have a lot to discuss today. But just see that in the radioactivity how we can calculate the lifetime of any particular living organism using carbon dating. Again, we have like if we do have two isotope and that have the mass number 35 and 37 and atomic number is 17, then how you can calculate the neutron? Because you know that atomic number is equal to atomic mass is equal to proton plus neutron, and proton is equal to atomic number. So this is how you can calculate the neutron. So this will be 18 and 20. Just see here. And the number of neutron is equal to mass number minus atomic number. So this is how you can calculate neutron of the isotopes. Okay, so till now we discussed the environmental chemistry part, but I know we have like 8 minutes, and we now jumped to the microbiology part. And because like my main motive was that because it has been 7 weeks that we have started the microbiology. So my motive was that we will try to I will try to give you briefly introduction of environmental chemistry, because it was like it has been 1 or 2 months that we covered that topic, and this is very recent that we started the microbiology. So okay, so that's why I allotted a very short time period for the microbiology part. Okay, anyway, so in that microbiology, we had a very popular question that how we will differentiate between two type of bacteria that are positive and gram negative and gram positive bacteria. So how we can do it using the cell wall of that. If we do have thick peptidoglycan layer in the cell wall, then we can tell that this is the gram positive bacteria. And if we have thin layer of the peptidoglycan, then we can tell that this particular bacteria is gram negative. You can just see here, uh, for the gram positive, we have 1, 2, 3, 4 layer of peptidoglycan, and for gram negative we have just one layer of peptidoglycan. So this is how we can differentiate whether the bacteria is gram positive in nature or gram negative in nature. Okay, the one very important in biology is the nomenclature or the scientific name. And this scientific nomenclature is also known as the binomial. So you have two names. The one is the genre and species. So for example, we are Homo sapien, then Homo is genus and sapien means genre. Sorry, Homo means genus and sapien means species. So this is how we can give the name of any of the organism. And but how we can write the name? So there is a particular rule to write the scientific name, and that particular rule is that the genus will be capitalized. So the first word will be capitalized and the species will be lowercase, and both will be italic in the italic in font. So let me show you here the name. So for example, the scientific name for tiger is Panthera tigris. So if you will see here, the P is capital, but for the tigris, T is small, right? So and the first part is genus and second is species. So this is how there is some rule to write the name of any particular organism in a scientific way. Okay, the next question is like this is related to the cell biology, and the question is how we can differentiate between eukaryotic genomes and the prokaryotic genomes. So, so the question is, which of the following is found in eukaryotic genome but not in prokaryotic genome? So these are the introns within the gene. Let me show you the one diagram. So you have DNA, right? The segment of DNA is known as gene. Okay, within that gene, we have intron and extron. So introns means these introns are not used for the protein synthesis, but these are used for the gene expression. And these are like a very repetitive segment that we have in human DNA, and that will mitigate the variation or mutation that we may have with the time. So these are very helpful for us, but these are not giving you the information about the protein synthesis. But these particular introns uh, are present only in the eukaryotic, but they are not present in the prokaryotics. So just see here, for mRNA only exon will be used and introns will be removed. Okay, so here again you can see in prokaryotic gene we have another type of like sequence, and for eukaryotic gene we have another type of sequence of the genes within the DNA. Okay, but very simple question. How you will describe a genome? So genome is nothing but the entire set of DNA that have coding and no non-coding region. So coding region are exon and non-coding regions are intron. So if we have that particular DNA that have both coding and non-coding region, then we call that particular region is genome. Here you can see, but I will not go into detail. Then, which component of genome is responsible for coding? And as I told you, this is exon, because introns will be removed. Here you can see we had the exons and introns, but there will be splicing using that spliceosome. These introns will be removed, and later on in mRNA there will be only exons. Okay. There is some virus there are some viruses that can infect the bacteria. So what how what name we can call to that particular viruses that can infect the bacteria, and these are known as the bacteriophage. Just give me 1 minute. So you have heard that the Ganga river is very holy in nature, very sacred in nature, and like very pure water we can have from Ganga river. And the main reason is that whatever bacteria that river have, they also like that river also have viruses, and that viruses that can infect the bacteria. It means bacteria or any infection, microbes can be killed or removed by the viruses that we have in the Ganga river. And that's why Ganga river is very sacred in nature, because that river have a multiple variety of bacteriophage. It means that particular Ganga river has the viruses, that viruses can infect infect or kill the bacteria from the water body. So that's why because just of the bacteriophage, the Ganga river is very holy in nature. So the answer will be bacteriophage. We talked about the active transport and passive transport. So, if we do have cell and if we need to transport within the cell something, then there is a two type of transport, active and passive. So, if you need energy for the transportation, then this is active transportation. And if we do not need any kind of extra energy for the transportation, then this is passive energy. And diffusion, osmosis, these are the part of passive passive transport. But if we do need ATP, then this will be the part of the active transport. So and aquaporins are some kind of protein that will facilitate the transport, and that will be the part of the passive transport. You can just see here how the aquaporins can help to transport the water within the cell, and this will be the part of passive transport because we are not utilizing ATP. Okay, if what kind of staining technique we need to stain, and or what staining material we can use to differentiate whether our bacteria is gram positive or gram negative, then we will use the crystal violet stain. You can just see here, if it will be the gram positive, later on after staining it will give you the purple color. But if that bacteria is gram negative, then that bacteria will give you the pink color after staining. And that's how crystal violet can be used to differentiate between whether our bacteria is gram negative or gram positive. Uh, then which macromolecule is essential for the protective coat of viruses? So viruses have that particular coat that can protect that viruses from any kind of extreme condition, and that coat is made up of protein most of the time. You can just see here, if it is a virus, then virus is covered with a protein. Okay, so yeah, so we have one organelles within cell, and that organelles is mitochondria. Mitochondria has its own DNA. No doubt, cell has its own DNA, but within cell we have one organelles, that is mitochondria. Mitochondria also have one DNA, and it is believed that once upon a time one prokaryote was eaten by another prokaryote, and this is how mitochondria was like prokaryote that has been eaten by another cell. And that's how this is endosymbiosis theory. You can read later. So about endosymbiotic theory. So it was just like that. We had the cell, and it is believed that one prokaryote is entered into the cell, and now that prokaryote is nothing but the mitochondria. I think time has up. Just give me 1 or 2 minutes, then we can end this. Then how you can tell that this is the nuclear? Okay, nucleotide is a very basic component of the DNA, because DNA is made up of nothing but uh, DNA is made up of nitrogen base, sugar, and phosphate. And here we need to find out the wrong statement, because in nucleotide of the DNA, we have the sugar, and that sugar is deoxyribose sugar, but not the ribose sugar. Sugar is present in RNA, but not in DNA. So that's why C statement is wrong one. And what statement is false about the plasma membrane? Then plasma membrane is semi-permeable, means some of the compound that plasma membrane can allow to enter, but some of the compound it will not allow to enter. So it doesn't mean that it is resisting all molecule to enter and leave, but this is semi-permeable in nature. So that's why C statement is the wrong statement, and that's why this is the right option. Then coming to the anabolic and catabolic reaction, then anabolic means the reaction that will consume the energy and will form some compound. Some we had basic compound, and then that will make the complex compound. But if we are talking about the catabolism, that will release the energy, because complex compound will be broken down into smaller compounds. So this is how it will release the energy. Just you can see here, glycogen to glucose and glucose to glycogen. So there is the catabolic and the anabolic reaction. Okay, whenever we need any extra energy for any kind of reaction, that energy is, most of the time, that energy is in the form of ATP. Okay, so this is adenosine triphosphate. And whenever we need energy, then what we do, we break down the ATP, and here the phosphate and oxygen bond is very strong, and it will release enormous amount of energy. We talked about substrate level phosphorylation. I know this is not like I can't explain much about this, but this is low level phosphate bond that are formed in ADP, and this is how we can do the phosphorylation. You can read more about this. I already have explained in previous slides. Then what kind of fungus or fungi we need to ferment the grape juice to ethanol for wine or beer? So this is Saccharomyces cerevisiae. So this particular fungi is used for the fermentation. Okay, the one important term is bio concentration factor. So bio concentration factor is the concentration of that particular compound that we have in the body, as comparison to the concentration that we have in the water. So this is bio concentration factor. So the concentration in organism versus concentration in environment. If we are talking about the bioaccumulation factor, so with the time, how within particular organ that compound is increasing. So this is bioaccumulation factor. So how that particular compound is increasing. Then another important terminology is biomagnification factor. So this is with increasing the trophic level, how the concentration are increasing. So this is biomagnification factor. So just see here, in fish we had a small concentration, but in large fish and fish eateries bird we have the large concentration. So this is how we can differentiate this. I think we should skip, and time has up. So let me please complete this. I had just 5 or 6, but let me go to the last slide. So thank you so much, guys. This slide is also has been uploaded on NPTEL, so you can watch, you can read. And thank you so much. And I also want to wish you all the best for your exam. Like either you will appear for this particular environmental chemistry and microbiology exam or not, but here's you must be student, and you must will have some exam in which you will appear. So all the best for your exam. And thank you so much for showing me the patience. And this is how like this course is finished. Thank you so much for like every week coming for this live session. And yes, thank you. Now you people can leave and have a good dinner.